Okay, so today we are going to learn about object detection. So far, what we have learned is the basic of this convolutional neural networks and how people have used those neural networks for image classification task with some case studies like AlexNet, BridgeNet, ResNet, and GoogleNet, and some combination of them in the last session. So from today, we are going to start the second stage of this course, which is learning some particular computer vision problems and how we are going to use machine learning or deep learning for those tasks using some of the representative works in this area from the last like 5 to 7 years. So in these days, there may be some more advanced works, but we are going to learn most basic and fundamental works, which provided the basic idea that we are currently using as our basis. And understanding these will be helpful for you to read more recent papers in each of these topics. And as the first topic today, we are going to start with object detection task. So let's start. So far, what we learned was image classification. So what is the image classification task? Given one image as an input, and we have a set of labels that is predetermined, like 1,000 classes for ImageNet dataset, for example. And the task was assigning some scores or probabilities of each of these labels, and we output a list of correct labels corresponding to this image. And for example, for this one, we would like to output cat as our answer using our model. So that is the image classification task. Usually, we expected a single main object, and no spatial localization was needed. What does that mean? In this object detection task, we are going to find out all the objects corresponding to each of these classes defined in our vocabulary, and we would like to locate it where it actually located within that image. For example, for this given image, we'd like to locate all the persons, because person is one of the class in our vocabulary, and kite is another thing. So we'd like to find out all of these kite and persons and locate them. And optionally, but usually, we output the scores or the confidence scores for each of those to be there. So for example, here, expected output is a list of entities with classes for each of these, which is a list of objects and what class it belongs to, according to our prediction. And the bounding box, which is covering the entire object as tight as possible. And the corresponding confidence score, like this one is kite, 99% for sure. And this one, for example, this is very small, and this model outputs like 54%, something like that. So basically, we'd like to estimate two things. Where is the object, and what is that object? And in this image, for example, we see some houses or trees, but probably that's not part of the vocabulary, so we didn't detect them. So basically, this is the object detection task, and we are going to study how to tackle this problem today. Object detection data set looks like this. So the left figure indicates the high-level idea of that. So in this image, we have two objects. One is person, and the other is dog. And we have these locations. So here, the size is just the size of this image. And depth is the number of channels. And here, object, we have two objects. One is dog, the object name, and the other is person. And we have the bounding box here. So bounding box components, always we have 4 components, sometimes in a different way. So for example, in this one, it specifies the leftmost and the topmost XY coordinate, and rightmost and the bottommost coordinate of the other points, something like this. So specifying these 4 coordinates, we can actually specify the bounding box. Bounding box is always a rectangle, and that is specified by these 4 numbers. So in this data set, it provides x mean, y mean, and x max and y max. Okay. Or another way of doing that is providing one points, which can be a center point like this, or one of those corner points, and width and height. So with these four numbers, we can also specify this bounding box, right? So some data sets provide this x, y, w, and h, and some data set provide this x mean, y mean, x max, y max. And you can actually convert one from each other using some simple math. So either is fine. And these two are most widely used object detection data set. These days, there are some more larger data sets, but you're going to see these data sets a lot in the papers that we cover in this class. So Pascal VOC, they have multiple versions. 2007 and 2012 are most widely used. They have about 10,000 images and about 27,000 annotated objects on those images. And they have 20 object classes, which is marked as the orange in this image. And MS COCO is much larger data set with 300K images and about 2.5 million labeled instances on 80 object classes. So this is much larger data set, which is used kind of a standard for our pre-training models recently. So yeah, you are going to encounter these data sets more very frequently when you read these papers. So how we can tackle the object detection task? So here's the very first idea we can actually try. This can be seen as a classification plus localization problem. And we know how to do object classification, image classification, as we discussed so far. So maybe we can do something similar. So given an image, we have two things: the class and the location, the bounding box, right? So given these ground truth labels, we would like to output this. This is cat, and the cat is located from this location, x point y, and width and height. So what should we do? We may train some CNN, and this is an Rcnet, as you know. So we just feed this image to this model, and then it finally outputs some classes. That's what we've done so far, right? So given the fully connected layer, we do the score for each class, and after the softmax, we have the probability for each of those classes. So we use the cross entropy to find out those correct class. So this is exactly what we have done so far for image classification task. In addition, what we need to do is localization. So because these localization ground truths, x, y, w, and h, are real numbers, this is more like regression rather than classification. So we conduct simply just regression problem. So after this, we map it to four numbers, x, y, w, h. And we have the bounding box ground truth, which is also four numbers. So we compute the L2 loss or squared loss. And we can just simply solve the regression problem. So maybe that's doable. And because we have two loss functions at the same time, these are added with some weights, and we just minimize the total loss. So this can be one of the multitask learning. So this idea may work, just looks okay, but there's a problem. We don't assume that there's only one object in each image. So in each input image, we may expect actually multiple objects, and our task is actually finding out all of them. So ground truth label is a list of these. For each of these objects, we have what is it and where is it. And for each image, obviously, we have different number of objects. So if we just feed them, and then for the classification loss, the classification score will be a multiple of them will be 1, should be 1. So how should we minimize the loss? The ground truth label, should we just give one-hot encoding for each of those multiple objects? Then they should be summed to 1. So that means the threshold for each of those objects should be Oh, can you hear me? Okay. I don't know why. Okay, sorry about that. Is it okay now? Okay, thanks. Yeah, so for this multi-object detection task, we have unknown number of ground truth objects. So for this regression part, each of these ground truth objects should have 4 numbers, but we don't know how many objects that we are going to detect from this image. So uh, it's weird because after the fully connected layers, how many nodes should we have? We cannot pre-decide it. And some images have just one example, one object, and some may have like 100 of objects. So it's really hard to actually design this model with some fixed number of values. So multi-object detection is a little bit tricky to tackle in this way. So how should we do that? Yeah, each image may have different number of objects here. So a brute force idea initially was like this. We apply a CNN classifier with the class, all the classes plus nothing there to many crops of the image. For example, for this image, you apply some method to find out some potential bounding boxes like that. Somehow you have that. We are not going to go to the details of that, but there were traditional computer vision methods that propose the bounding boxes. That's something probably there. So you just do that, and then for each of those sub-images, you feed them to some convolutional neural nets, and then you classify them. So it may correspond to all of these, one of these objects in the vocabulary, or none of them. So you can do that for all of these proposed bounding boxes, and then you will have the list of scores, the classes with high scores. Then you just collect all of them. Then that will be the final list of the detected objects. May work. What's the problem with this? Computationally too expensive, obviously, right? You have to find out all the possible bounding boxes in the image, and you have to feed them all of those individual images into this network, and have to compute all the probability, and then choose only some of them based on that, which is really inefficient. So we can't basically try all possible crops from the image. You have like 300 times 400 pixels in the image, and all possible bounding boxes in the image is too much, right? So there are basically two directions of doing this. One is proposer-based methods, and the other is proposer-free models. Or in other terms, the first one is called two-stage model, and the other is called single-stage or one-stage model. So in the proposer-based or two-stage models, it basically consists of 2 steps. One is the region proposer. So it tries to actually find out these bounding boxes more efficiently and more accurately, and more with less number of them, but with higher accuracy. That's basically what we would like to do with the region proposer. And then for each of those regions, we are going to recognize what is that object and where it is. We actually basically adjust the bounding box location. So basically, these proposer-based methods is based on 2 steps. One is the proposer of the regions and recognition within the each of those proposers. So here we are going to learn these 4 methods: Rcnn, we just run. Okay, this is a serious problem. Okay. Okay, so Rcnn part. So we in the proposer-based method, we are going to use learn Rcnn, fast Rcnn, and faster Rcnn. All of these three are same family of those methods. And Rfcn is more advanced model based on those. So we're going to learn these 4 models for the proposer-based methods. And proposer-free models, basically, it's a single-stage model. And in one step, actually, it does all the proposers part, region proposer and object recognition at the same time. So here, we are going to learn YOLO and SSD in this class. So let's start with the proposer-based method. Any questions so far? So far, so good? Okay, starting from now, it will be a little bit harder. So Rcnn, let's start with the Rcnn. It stands for regions with CNN features. It's not recurrent or something related to Rnn, but it's basically the regions with CNN features. And it's a very first deep learning-based two-stage model. So we have region proposer plus recognition each stage. In the first stage, it's a region proposer. So this method actually doesn't propose anything for the region proposer, but they use some existing methods. So selective search or edge boxes or MCG, these are pre-existing region proposer models. And given an image, it proposes all the potential bounding boxes with some objects within that. But these are quite slow. For each image, it takes like 0.2 seconds to 2 seconds, which is really long. So if you would like to process with like 1,000 or 10,000 of images, then yeah, it will take much longer. But yeah, at that time, these methods were used as kind of standard. And at that time, those region proposer was not just slow, but also their confidence was lower. So at that time, they had to propose actually a lot of images, a lot of patches within the image. So on average, they propose about 2,000 bounding boxes, potential bounding boxes. And based on that, they conducted object recognition on those about 2,000 images, sub-images. And actually, once we have these proposers, then after that, it's very straightforward, right? You can use any CNN to extract the image patch feature, and then you run some classifier on top of that, and they actually use support vector machine to map the features to labels. So here's an example. Given an image like that, we run pre-existing region proposer networks like selective search, and it provides about 2,000 potential bounding boxes for each of these objects within the image. So for example, we have these 5 bounding boxes from this image, and then we resize all of them to some predefined size to be the input for our neural networks. So this is just deterministic function. And then we feed each of those image patches to our CNN models. So suppose that can be an AlexNet or a VGG, and they use actually the VGG. And then we finally have some features at the end, right? And then they train some classifier, which is the SVM. So given these features, what is that? And then some label data set, they actually trained what are them. And that's just K plus one-way classifier. K is the number of possible examples, which is 20 for Pascal VLC 2007 data set. And none is just one more. So they can be none of them, right? We are just detecting only 20 types of the objects. So that can be none of them, even though it's an object. So they also add the non-class. And after that, for example, this one is sofa. So we have a high score for the sofa. This one is lady, this is laptop, and this is mobile phone, but it's none of these. So it's not none, something like this. And for this detection task, we not just to classify them, but we also need to locate them. So if the selective search is perfect, actually we are done because we already have the bounding box for each of these objects. But if that's perfect, we are done. But what about it? It's not perfect. So we regress the bounding box not to find out the actual location of them, but we adjust its proposed location. So for example, this one should be moved to the right for about 3 pixels and move up to like 10 pixels, something like that. This example, actually, we have the bounding box almost perfectly, but something like this. We have to resize the width to 10% larger and 2%, the height should be 2% smaller, something like this. We have to readjust the bounding boxes to make it perfect. So let's talk more about that in more details. So classification is straightforward. That's what we've done in the image classification. But bounding box regression is a little bit more complex. So from the last features of the proposer networks, let's say that's P. And we have the bounding box candidate, which is Px, Py, Pw, and Ph. So given that, for example, the center point of here, this image patch, is Px and Py. And Pw is the width of this image. Height is the Ph is the height of this image. So we are given those 4 proposers points. And in training, we know it's ground truth bounding box, so x, y, and wh. And our task is train some model to map this p coordinates to this g coordinates. And we'd like to train some small regressor to readjust these to be more realistic to according to the ground truth. That's basically what we do here. So I wrote here, regressor learns scale invariant transformation between 2 centers, log scale transformation between widths and heights. What does that mean? Let's see. We are given the x and y score, the coordinates, not score, sorry. It's the x and y coordinates, which is the center of the bounding box. In the proposer, this black box, we have this px and py, which is its center. And we know the ground truth x and y, which is located in this red box. So the center point is different by this, and by this, x and y. So if we make this simply, actually, what we need to learn is px plus something, py plus something, and those something needs to be regressed. That's what I actually mentioned here, just plus 3 pixels minus 10 pixels, something like that. But they actually made it a little bit more complex. They mentioned that it's scale invariant. What does that mean? Some objects is very huge, like this lady here, or this sofa, which is relatively large in this image, versus very small images like this. This cell phone is very small. Some objects is very large, some objects is very small, even though they are in the same category. So some person can be pictured very large at the center, some picture maybe in the background and very small. So the scale of each object can be very, very different in an image. But if we learn how much we have to adjust the scale in an absolute scale, which is the number of pixels, that will be very different, right? For some center person with large scale, moving like 5 pixels is nothing. It's basically just a small movement. But in the small person at the background, moving 5 pixels will be like several steps away. So they would like to learn this movement scale invariant. So it's a relative to the actual size of these bounding boxes. So they multiply the width here and the height here, and they just regress this part. Then this will be the scale, multiply this the original scale of this bounding box. So for the larger ones, they actually move larger, and for smaller boxes, they actually move smaller. That's why we multiplied PW and PH here. And this DP, can you hear me now? Can you hear me now? Okay. yeah, let me repeat this part. dxp and dyp is our model, and our model will output something. The x, how much we have to adjust with the x given this p for this one. We multiply its scale, which is the width, and then we move add from the actual previous px in the proposer. Then we hope that that will be the ground truth of the x coordinates. And same thing for this y. So this dp is our model, and we would like to adjust the proposed coordinates to the ground truth coordinates we observe in the training data set. And for this w and h, which is the scale of this bounding box, with pw is this, and ph is this, and we would like to adjust it to be more realistic, which is this red box here. How much we have to expand it or shrink it? So we multiply our adjustment to the original scale. But here they also add this exponential, because otherwise this will be scale will be too small. So regression doesn't really work because of the noise. So somehow they added this exponential function here. Then this will be the log scale of the actual adjustment. Then we can play with much larger scale more robustly. So it's just there to make it more robust. So here, this t, x, y, w, h is the target value that our model needs to actually regress. So we can just solve for this one. Then you move this px to here, and divide it by this pw. Then dxp should be this value. So that's why we call this target x. And target y in the same way. Target w and h also the same way. You divide by this and log on the both sides, then you're going to have this one. So these are the target values that your model, which is dp, are going to regress. And this ti is used kind of the ground truth values. And our model, dip, will output 4 values. And we basically solve it by squared loss like this. So basically, it's a regression problem. OK? This looks a little bit complicated, but once you understand, it's basically nothing. Just given a proposed bounding box, then you have to adjust it to make it more closer to the ground truth bounding box. And they learn how much you have to move, translate, and expand or shrink the bounding box to make it to red. OK? OK, so here's the summary of the Rcnn. So this was the first modern deep learning-based image detection model, and significantly reduced the computation from force method, which we never use, actually. And assuming that given region proposer model actually works well, then detection performs OK. So this is the very first model that we learn in this course. And this one actually has some problem. So still computationally very expensive, mainly because of that selective search or the region proposer models, because we have to output like 2,000 independent 2,000 image patches, and we have to resize them, and then we have to feed all of them to extract the features for each of them independently. And inference 2,000 images is not a trivial work. So Rcnn is super, super slow, and people have tried to improve its speed. And the first successful work was fast Rcnn. So they tried to reduce the main bottleneck of Rcnn, which is extracting the image patches, and then they had to extract image CNN features for each of them sequentially or in parallel. But in fast Rcnn, they actually just extract CNN features only once with the entire image. And then because our CNN models are the convolutional feature space, which is location aware, we can use those conv features to do something after that step. So that is their basic idea. So the inference is just reduced from 2,000 to 1. And then after that, we just use those conv features to do something after that. Here, the region proposer, they didn't change anything from the Rcnn. So they just used the off-the-shelf method like selective search. And after that, we do the object recognition, which we just do the just using the entire image to extract the conv features just once. And then this is the main idea. They perform region of interest pooling, ROI pooling. We are going to pooling, and then how to this is a real problem. Can you hear me now? Can you hear me? Okay. Yeah, I have to find out what's the problem. Actually, from today, I'm in the California, and I'm using my internet at my home, which is unreliable. So yeah, sorry about that. I'll try to find how to fix this. In the last semester, this was better than SNU network, so we didn't have any problem. But this semester, I don't know why. Yeah, sorry about that. So yeah, I didn't talk about that much during this connection. So we are going to learn how they actually apply this ROI, region of interest pooling, in this fast Rcnn model. So again, we are given this image, and then they extract proposals in the same way using the selective search. And then instead of resize this and feed it to CNN independently, we just extract the CNN features for the entire image just once. So here, suppose this is our final CNN map, like conv5 features. From here, we just map these yellow boxes in the same scale to this this image, because this conv feature actually reflects the location and the features meaning of those corresponding locations in this image. So these bounding boxes should be also located in the same parts of this image, preserving its relative locations. So is this okay? Yeah. So we just map by just computing its relative location within this box. Then we somehow adjust its location to axis aligned to this final convolution feature map. And then we have to, eventually we have to output the image patches or feature patches for each of these sub-images. So what we do is, for each of those corresponding boxes, we take the corresponding boxes like that, and that is called actually region of interest pooling. So pooling, again, what was pooling in convolution? We take multiple values and then somehow aggregate them, right? So from this entire image map, we take the actual region that we are interested in. That is called region of interest pooling. So given this 8x7 map, we take this 5x4 subpart. That is what we call region of interest pooling. That's nothing, right? Because we expect that this object will be located somewhere here. We take the values and take this as a map. For this object, we take this part using region of interest pooling. Then we have this feature map. And then eventually what we need is the same sized image patches that we can run the classifier. Otherwise, we cannot train a classifier on top of these various sized patches. So we just map this to some desired size. For example, here I map to 2x2 feature maps. So you just divide it 5x4 to 2x2 like this, using some simple math. You can actually refer to the paper. They use 7x7, but in the same way. So overall, it's very simple. You just run the selective search to have the original proposer. And then after extracting the CNN features for the entire map, and you map these bounding boxes to axis aligned like this in this last feature map. And then you take the corresponding boxes using the region of interest pooling. And then you map it, remap it, or resize it to the desired final feature size, like this. And then after that, it's the same. You train some classifier on top of that to classify the image, the object in that box, and bounding box regression. So far, so good. Okay. So fast RCNN is accurate than RCNN, and it's much faster than RCNN. In the training, it's like 8 to 18%, 18 times, and for inference, it's like more. Drawback, or not drawback, but they actually didn't tackle the this. Okay. After that, I will try one thing. Okay, I will try to use a tethering using my phone. Okay, can you hear me now? Okay, hope this works better. Let's turn it again. So, here. What about now? Can you hear me? Okay. Hmm. Okay, can you hear me now? Let's try. So the fast RCNN was faster than Rcnn. It's more accurate, but they didn't tackle the off-the-shelf region proposer part. So it's still computationally expensive, and they that part was actually tried to be improved using the next model, which is faster Rcnn. So before that, I see some questions here. Does that approach not decrease the resolution of the bounding boxes because the output of the CNN is much smaller than the input image? The output of the CNN is much smaller than the input image. Dennis, what do you mean by that? Sorry, I can't hear you. Let me. I don't know why I can't hear you, but let's try this. Yeah, okay. Thanks. CNN have pooling layers. Yes, they have it. which makes the dimensions smaller. Okay. I think I understood. So in the later stage, you mean that we have like 7 by 7 output, right? From there, how should we uh, uh, adjust the bounding boxes in finer resolutions? That's what's your question. It just learns how to do it, given the even if it's a small dimension. Actually, it has the information what is the contents of that in a compact way, because it's a vector of like 512. Actually, the size is like 7 by 7 by 512, which is a tensor. And given that, each of those locations, it has the information, what is the contents of that particular location. Even though it looks like a coarse resolution, still we expect that it actually contains some finer details of that, what is the contents corresponding to that location. So from that rich information, we train bounding box regressor. And we train those regressor to actually regress how much we need to adjust the bounding box as we discussed before. So it is trained to make it happen. Okay, cool. Okay, let's move on. So after the fast Rcnn, actually here they only apply the max pooling to take this 2 by 2 to this value and 3 by 2 to here. They apply the max pooling, but it's a little bit related to Dennis's question. So it's the resolution may be too coarse. So in the mask Rcnn, which is advanced model after this, they propose to regress it, but apply the relative distance to convex combination of each of those four corners relation, the corners values to regress to these smaller maps. So we are going to use this for segmentation task, which we are going to deal with in the next as a next topic in lecture 10. So mask Rcnn is nothing. They just apply the linear interpolation instead of the max pooling to fill those feature values in the smaller dimensions. And we're going to see this again later. Okay, so faster Rcnn, which is we ask you to implement in the homework 2. So this part will be really important for you. So this part, they didn't change the second stage, which is the classification and regression and ROI pooling. Everything is the same in the second stage, but they tried to replace the selective search, which was super slow in the first stage, and they wanted to use this their own region proposer network, or RPN, in the first stage. So here's the main idea. For each position in the convolution feature map, they suppose a set of candidate bounding boxes, which is called anchor. And for each of those anchors, they have applied three aspect ratios: 1:1, 1:2, and 2:1, and three different sizes. So total 9 anchors were used. So these 9 anchors are used as a candidate anchor for centered at each of those conv locations. And if the anchor sufficiently overlaps with actual ground truth bounding box, then it is considered as positive. Otherwise, if that does not overlap at all, then it's considered as negative. And otherwise, if they just overlap a little bit, then they are just ignored. We are going to see some examples in the next slide. So they train this RPN to classify if these anchors are actually positive or negatives. And if it's positive, then they regress it to actual bounding box in a similar way to what we've done in fast Rcnn. Probably you don't understand what they actually do with this text. So let's see some examples. So suppose that this is the ground truth bounding box for this lady. And if our proposed positive, the anchor is like that, then this is considered as positive. How? We compute IOU. IOU means intersection over union. So area of union means for both of these bounding boxes, we take the union of those areas. And intersection is intersection, as in the set. So we compute this IOU score. So if those two of those bounding boxes are exactly overlapping to each other, then this score will be 1. If they don't overlap at all, then it will be 0. And if they overlap, it will be something between 0 to 1, like that. And if that's larger than 0.7, they take this as a positive anchor. So this positive anchor is actually positive or true for this ground truth of this lady. If another anchor is like this, then if the IOU is less than 0.3, then this is used as a negative anchor. But something like this, overlap between 0.3 and 0.7, they ignored. It's neither negative nor positive. So here's the region proposer network, how it works. Given this image, we extract the CNN features, as we've done in the previous model. And now we have this. And here, we don't have those proposed yellow boxes, right? So we cannot proceed without that. So what should we do here? Slide over the last conv layer, which is this one. And slide over means starting from the first one to second one to the last one. For every positions, we slide over with 3x3 spatial window, which is something like this, right? This blue box. So here, we map it to 256 dimensional using fully connected layer. So this one is an embedding of this 3x3 patch in our last layer. And then we regress to, or classify or regress to these 6 things. We classify if this blue box is a positive anchor. Here, is it? It may be right? Because it's overlapped with this yellow ground truth bounding box over like 70%. So this probably will be 1. And is this the negative one? Probably not, right? So this is positive and this is not negative. And this regression, this blue box needs to be readjusted to exactly match to this yellow one, which is actually here, to this one. So how much we have to adjust its center x and center y coordinates and its width and heights, exactly in the same manner as we've done using the previous model. So for this particular box, we output these 6 things. So we predict the probability of this input region to be a positive anchor, the first one, and to be a negative anchor, which is the second one. And it's also possible, actually, we just use only the positive, not negative. So it's the design choice, but we'll just follow what they've done using these 2 things. And then we regress these 4 bounding box coordinates. These are actually based, the same as before. And then I mentioned that we have 3 aspect ratios, which is 1 to 2, 1 to 1, and 2 to 1, which means the basic bounding box is stretched to have 1 to 2 ratio like that, and 2 to 1 ratio like that. And we actually repeat all of these three times like this. And I also mentioned that we have 3 different scales. So we shrink it to twice, and it's expanded to twice like that, red and green. And we repeat this 3 times for all of these 9 boxes. So overall, the number of outputs is 2k plus 4k. So 2k means k is 9 here. So we have 3 times 3. So we have 9 columns. And 2k means, 2 means this classification, positive and negative probabilities. And 4k means these regression bounding box 4 numbers. So we output 6 times 9, so total 54 numbers after this embedding. Okay, so in this way, what should we do after that? We will have the positive, the probability to be each of these bounding boxes will be positive. And if that's positive, then we use this regression adjustment to fine-tune this bounding box to regress it to the actual ground truth bounding box. And if that's negative, we just ignore that part. So here's the loss function they use to train the model. So they have both the classification part and the regression part. For the classification part, this y hat I is the predicted probability that the anchor is positive or negative. And for this one, they have the corresponding ground truth. So one, if the anchor is actually positive or negative, which we can compute using the IOU against the actual ground truth bounding box. And yeah, for this loss, they used log loss, which we learned in lecture 3, as far as you remember. And for this regression part, they have the BI hat is the predicted bounding box, and BI is the ground truth bounding box. And for this regression loss, they used L1 loss, but smooth L1 loss means usually the actual L1 loss is not differentiable at some points. So they apply some of the smoothing, but basically that's L1 loss. So they used some regression loss using L1 and compare these GT bounding box and the predicted bounding box. And they multiply yi here because these bounding box regression should be performed only we actually have the object there. Otherwise, this regression is actually not meaningful, right? So this yi term is multiplied here, and this is the ground truth. If the anchor is positive, then we actually do this. And here we multiply lambda, which is a hyperparameter controlling the relative importance between the CLS and regression. So it looks complicated, but each of these components is actually as simple as we've learned in the previous slides. And in practice, they extracted 256 anchors per image, and actually they actually have more than that because for each location they proposed 9 of them, but they sampled. But most of them are actually negative samples. In each image, we usually have just a few objects. So most of them are negative. So they sample positive anchors first, up to 128. And then the rest of them will be filled with the negative anchors. So that's their fine details of the implementation. Okay, so this part is a little bit more details about how they trained the faster Rcnn model. Ideally, they may just wanted to end-to-end train, but somehow practically it didn't work. So you don't have to memorize these things, but I'm just going to explain how they did. So at the first step, they just only trained this RPN. So initialize these conv layers with ImageNet pre-trained model, and then they trained only this part, this proposal part, the left part. And then they reset these conv layers to ImageNet pre-trained models again. Then they freeze this region proposal network and only train this classifier part, which is the same as fast Rcnn. Faster, not faster, but the fast, basically slower Rcnn. So second step, they only train this part. And then after that, they fine-tune this RPN. But now, instead of the conv layers they have trained in the first step, they use the conv layers trained in the second step, which is optimized for this classifier, not for RPN itself. So they fix this conv part now, and then based on these slightly different conv layers, they fine-tune this proposer. That is the step 3. And after that, we have the same conv layers for both of these networks. And at the very last step, they also freeze these proposer networks and only the fine-tune the classifier part. They did somehow like this and made it work. But after that, people tried to make this end-to-end trainable, and you may be able to find some existing source codes which can be trained in end-to-end. But that's what they have done in that era. So eventually, they achieved much faster speed compared to fast Rcnn. Faster Rcnn is much faster, especially in the proposer network, because this is the main change. And overall, the previous model was like for every second they processed about half frame, but now they can process like 5 frames. So it's much, much faster. Yeah, and that's the faster Rcnn parts. And let's move on to RFCN. We have to cover a lot of models today, so let's move on fast. RFCN is extension from the faster Rcnn in that they observe that each of those image features may be different depending on where it actually locates within the bounding box. So for example, here, in the image, suppose this is a bounding box. We don't see anything here, but suppose this is a bounding box, then it will be mapped to here in the feature maps we extracted using the CNN. Before, each of these channels didn't have any meaning or order. It was just multiple like 512 features. The order didn't matter. But this time, actually the first one, they optimize to the values that this will be the representative values if this is located as the top left within the bounding box. So for this part, we refer to this top left channel to fill that value. And the second part, which is the top center, we have its own designated feature map. And for the second part, because it's the top center within this bounding box, we take its value. So this color corresponds to each of these channels here. So this is position-sensitive score map. So the channels are divided by its position within the bounding box. So the main motivation for this is, okay, so here, if this class is a person, then we know that usually a picture of a person, it looks like on the top center, we have a head and the face. And then in the below, we have shoulder and the torso and the leg in the bottom. That's user position of the human within the bounding box. So they try to take advantage of that fact. So if the face, actually the feature for the face part is learned mainly in this top center channel, for example, because human face is usually located there. Not always, but in common cases. And the legs may be located in the bottom. So the leg features are more focused and learned in these blue channels, something like that. So here's an example in their paper. So we'd like to detect this baby here. And for each of these feature maps, this is the top left feature map. This is top center feature map. And for each of these locations, they actually take the values corresponding to its relative location within this entire bounding box, like this. And white means it's a good match, and black means it's a bad match. So if we take these corresponding locations, we see that each of these are all whites, which means it's a good match. And we know that this baby is located like this. So this bounding box is good, as we see. And the feature map is also well trained, so it looks all white. If it's shifted by once like that, then we know that we see that actually this bounding box is not a good match with this baby. And now see that this part, previously we take this part feature from this top center, but now we are taking top left feature of for that part, which is not a good match because we don't see any. We expect something like this. It's a background, but we actually see the face of this baby. So this is not a good match, and so on. So for each of these feature maps, the values taken are mostly black like that. So eventually the vote is no here. So I just explained with some examples, but this is very simple extension of the previous model. But each of those feature maps are position sensitive, and they use this idea to improve the performance a little bit. And after that, a lot of proposal-based approaches were proposed, and we are not going to deal with these things in this class. But if you are interested in, actually the last paper, which is the object detection in the last 20 years, it summarizes all of these methods and recent models in more details. So you may refer to these papers if you are interested in. Okay, we have 3 more minutes, but okay, let's try to cover this YOLO a little bit. What is YOLO? We usually say that you only live once, but in here, the YOLO means you only look once. So instead of the 2-stage models, they apply only once the model, and we actually do the both steps, the region proposer and localization and classification, everything at once. So YOLO is one of the most popular method in this domain. So this is a single neural network to predict bounding boxes and class probabilities from a single evaluation. And everything is a regression. So we're going to see what's happening there. So another complex explanation of this, but let's see that. They divide the input image into S by S grid. They use 7, so 7 by 7 grid. And if the center of the object falls into the grid cell is responsible for detecting that object. Because we don't have the proposer here, now we need to assign each of these ground truth objects to be discovered by each single grid position, and we have 49 of them. So they use the center as its responsibility. And for each center location, they propose up to B bounding boxes. And actually, they use 2. So each of these objects may coincide to the same center up to 2 objects. So for example, in this image, the mom and the baby is almost located in the same center. So the center cell is responsible to detect both the baby and the mom. But if they have actually more than 2, then they may miss one of them. So B is equal to means that up to 2 objects may coincide in the same cell. And for each bounding box, we predict 5 things. The 4 of them is the center coordinate and the width and height, as we usually do with the regression. The last one is the confidence score. Confidence score is actually the probability that we actually have something of some object inside that box multiplied by the IOU between the predicted bounding box and the ground truth bounding box. So yeah, we'll see this in the later slides. And also, for each of those grids, they output C conditional class probabilities. So C is the number of classes, which is 20 in this data set. So they output 20 probabilities that the object there, it belongs to that particular class. So total number of output is 5B plus C for each grid cell multiplied by 7 by 7, which is the number of those grids. So this is the essence of this YOLO algorithm. So in the input image, they predict the bounding boxes centered at each cell. So total 7 by 7 times 2. So they have 98 bounding boxes centered at each position like this. This is basically regressed, not using region proposer network as in the 2-stage models. And then each of those cells, the object within that corresponding bounding box is classified into one of those 20 classes, and it is colored here. And then they apply something called non-max suppression to output actual bounding box like this. So what is those non-max suppression? This is really simple algorithm. So suppose we have, these are the set of the bounding boxes we have after that step. And then they just greedily choose the top one, which is the box with highest objectiveness score, which is 96% here, this person. And then compute IOU between this one and all other boxes to remove these red and yellow ones, because these are too similar to this person. So actually, you see that a lot of boxes are predicted to detect the same items here. So we just want to have only one of them as the representative one. So they applied this kind of logic to remove these 87% and 82% boxes. And now we have just these 2. And they repeat actually these until they don't have any overlapping boxes. Actually, yeah, this one, 98% is the highest one. So actually, yeah, they detect this first one, and then they remove these overlapping ones, and the same way they remove this human multiple boxes, then eventually they have just these two. So this is widely used not just in the YOLO, but other detection methods. They actually use this to remove these redundant boxes. Okay, yeah, let's try to finish this as soon as possible. Yeah. So this is the loss function of the YOLO. So here, the first part is the regression of the location and the bounding box size. So they multiply the when the sorry. So this I is the 49 locations, and J is the bounding box 1 and 2. So for each of those locations, if they actually have the ground truth object there, then this regression becomes valid. Otherwise, we don't do this because we don't have any object there. So the first part is the bounding box location regression using the squared loss. So x hat I and y hat I is our estimated coordinates. And these xi and yi are the ground truth location of the center. So they regress the location. And this is bounding box size regression. So instead of the exponential in the fast Rcnn, they use the square root for the same philosophy. So they do this as the regression part. And then they multiply some weight for this loss part, which is for this coordination part. And then here, confidence score regression. So if we have the object there, so if that particular bounding box actually has the ground truth objects, then the weight is 1 here. And the next one will be no object, and it will be multiplied with some value here. So here, what they do is the CI is 1 because we have the confidence score should be 1. We have some actual object in that bounding box. So confidence score should be 1. And our estimation is regress to be 1. And here, we don't have any object. So the confidence score should be 0 here. And if it's larger than 0, then we create some loss using the squared loss. And as I said, we multiply with some weights, which is smaller than 1. So positive is actually more important to actually detect something. But negative is more dominant, and it's less important. So they apply 1/10 multiplied here. And then last one is the classification part. So for each location, we have the predicted classes. And if that's not correct, we have the squared loss generated here. So everything is actually regression, as you see. So they actually combine bounding box location and size and confidence scores for object existence or not. And if it exists, then what is the class? So they actually combine all of these at once using this loss function. Let's stop here. This is the result. Actually, you can just read, and they basically say that it's faster and more accurate. So yeah. Next time, we are going to talk about the SSD and move on to the segmentation task. Okay, thanks for staying longer. And if you have any questions, you can ask now.